Hello, everyone, and thank you for joining our presentation today. My name is Jasmine Badiee, and I'm a fourth-year PhD candidate in engineering with an energy systems emphasis. I'm at the University of Georgia, and this presentation involves my dissertation research that I conduct with Dr. John Schramsky. Before we begin, I'd like to provide an overview of our presentation. I will start with an introduction to this area of research, followed with a literature review. Then I will describe my contribution to the literature, spend some time defining terms. After that, I will report my results, conclusions, and considerations for future work. In human society, we harness energy gradients to produce work and improve our human quality of life. Decades of this pursuit have brought about the age of the Anthropocene, which is characterized by exponential growth in energy, as shown on this graph on the left. We effectively believe that energy is the forcing function behind the exponential change seen in socioeconomic indicators, for example, shown on the right. The ultimate conundrum of energy is that it is highly correlated with both human progress and environmental damage. Human society has exceeded 3 out of 7 planetary boundaries to date, as quantified by Rockstrom et al. And shown on this right chart. The charts on the left show that similar hockey stick pattern that we saw in energy consumption, again, just showing that energy can be considered the forcing function behind these significant levels of change that we are seeing. First, though, let us address the human progress component of energy. My research focuses on quality of life metrics such as nutrition, life expectancy, etc. As you can see on these figures, when comparing power consumption on the x-axis with different quality of life indicators on the y-axis, there is a saturation effect, where there is a fast rate of gain initially, then some slower growth, then a leveling out. This relationship effectively shows that there is a possible similar social benefit at reduced energy consumption scenarios. This concept is not new. Many researchers have been exploring this phenomenon and suggesting ideal energetic scenarios for the purpose of maximizing quality of life and minimizing environmental damage. These studies date back as early as 1985, in which Goldenberg et al. Suggested a reduced power scenario of meeting all basic human needs with just 1.2 kilowatts per capita, or 0.32 terajoules per capita. However, power consumption alone does not tell the whole story. For example, let us compare the US and Saudi Arabia. When we compare the two on power consumption alone, they're identical, 0.29 terajoules per capita. However, we know the two societies are vastly different from one another, geographically, population, and even in their climates. For example, we can take that a step further with O'Neill et al. 2018's data. We know that the US has exceeded all 7 planetary boundaries, and that we have achieved 9 out of 11 social thresholds. Saudi Arabia has exceeded 6 out of 7 planetary boundaries and achieved 6 out of 11 social thresholds. Again, taking it back to population, we see a difference between those and in sheer land mass as well. We cannot use current power consumption in this case to differentiate between these two countries. We know that energy consumption causes change in the system in which it is expended. When we expend energy within that system boundary of a nation, for example, it ultimately changes the fabric of that nation. In countries like the US and the UK, where there is a history of consuming significant amounts of energy over very long periods of time, this has a accumulating effect on societal structure and on environmental damage. For this reason, energy expended in the past is still relevant to our current situation because it may have been expended to create a structure or a mechanism or a service within society that is influencing current quality of life. There is a knowledge gap that exists for a means to evaluate countries' economic, ecological, and social structures based on historical power consumption. For this reason, I've created a metric that I call embodied energy. As we now see, when we compare the US and Saudi Arabia on embodied energy, there is a differentiation that can attest to some of these other factors. So let's dive a little bit deeper into what embodied energy means. I define embodied energy as an accounting method for the change that occurs in a society when energy is expended within it. This change is in the form of structure. Structure can be tangible, buildings, transmission lines, roads, or intangible, like government and education. Maintenance energy is a concept you're all familiar with. It's the power consumption of a country. Power consumption is used to maintain structures created by past energy investments. The concept of structure and maintenance energies can actually be related back to Odom's work in strategy of ecosystem development. This figure is a model of how energy causes change within a forest ecosystem. You can see that initially, the rate of change of respiration is high and increasing. This causes biomass, the solid line, to also increase at a fast rate within those early decades. This is establishing that structure of the forest. We see energy being expended, R, and becoming embodied or invested within structures, B, such as trees, branches, leaves, wood, etc. As the ecosystem becomes more mature and established, this respiration rate begins to slow down, and so does the production of biomass. Respiration at these later decades becomes devoted mainly to the maintenance of the existing structures rather than for the purpose of developing new structure or increasing that biomass. Like forests, human society also involves expending energy to develop and maintain structures. Rather than tree trunks and branches, our structures look more like buildings and service systems. But the parallel of energy being expended to create structure and then maintain it is still there. Ultimately, we can boil the relationship between energy, structure, and mass down to this chart, where energy is consumed to arrange mass into structures, which then continue to consume energy. The fundamental difference, however, between human societies and forest ecosystems is that trees know when to slow the rate of respiration to moderate energy use. Human societies have no control in place for this. So, what is the relationship between energy structure and maintenance energy in human societies like Odom has shown for natural systems? This brings me to the results portion of this presentation. This graph shows the relationship between embodied energy and maintenance energy. Each point on this graph represents a country's values. Embodied energy is calculated as the cumulative energy consumption from 1820 to 2014. We have historical energy data for 65 countries. The maintenance energy values come from World Bank and are from the year 2014. For the most part, to be able to expend more energy for maintenance, you must have an initial investment put into place. And this makes intuitive sense, right? Because, for example, you can't burn significant amounts of fossil fuel energy if you do not have the infrastructure in place to do so. This data generally is not too varied and stays near the curve. However, we do see some outliers. For example, Saudi Arabia has a high maintenance energy relative to those in similar embodied energy values. The UK has a low maintenance energy related with those in similar embodied energy values. These variations can be from a lot of different things. Could be related to physical size or location of the nation, their climate, the makeup of their economies even. Next, we wanted to see how embodied energy affected other important indicators. For example, power consumption has been known to be correlated highly with GDP and environmental damage. We wanted to explore this relationship for embodied energy to see if that prediction is actually improved at all. So this chart on the left depicts trends for the world. So each point represents data for a year between 1971 and 2014. Ecological reserve is defined as a country's normalized biocapacity minus their average ecological footprint. The reason you are seeing negative values for this metric is because the planet has been in an overall ecological deficit since before 1971. Again, these charts show that conundrum of energy, right? As increases in embodied energy are highly predictive of increases in GDP, they are also highly predictive of decreasing ecological reserve. When comparing this to the more traditional metric of power consumption, which is this chart on the right, we actually see that the R-squared values for power consumption are lower when compared with those from embodied energy. Now that we have begun to establish embodied energy as an indicator, I want to turn our attention to energy's effect on societal structure. I hypothesize that embodied energy can be an indicator for the development of social provisioning systems of countries. For social indicators of quality of life, we again use O'Neill et al. 2018's data from their Nature Sustainability paper. This data includes these 11 social indicators. For this chart, I took every country that had 0 thresholds achieved, averaged their embodied energy value, plotted it. Every country that had 1 threshold achieved, averaged their embodied energy values and plotted that, so on and so forth for all threshold values. So what this chart tells us is that embodied energy is highly predictive of the number of social thresholds achieved. They even seem to form these distinct clusters with energetic gaps in between them, as shown by the different colors and the arrows. Interestingly, we also noticed a pattern in the order by which thresholds were achieved. This tier 1 is associated with this first cluster of red, tier 2 with this magenta cluster, and tier 3 with this green cluster. The first tier could be thought of or grouped as the needs of the individual, things related to individual success, such as income and the ability to have access to energy. The second tier are more communal needs, services that are generally provided at that community level, such as sanitation infrastructure and education. The final tier are these higher order needs that come after individual and communal needs have been satisfied. There are only 3 countries that have achieved all 11 thresholds, so it's not that we define development as achieving all thresholds. Putting all of this together, we hope to suggest a level of energy consumption for both embodied and maintenance energy that can provide for high societal advancement. In conclusion, embodied energy can fill a vital knowledge gap for the measure of energy structure while improving the method for direct comparison between nations. We have shown embodied energy to be more predictive of environmental damage and of economic growth than traditional power consumption does. Lastly, embodied energy helps predict the general order by which social thresholds are gained as society moves towards development. Plans for future considerations include making an official recommendation for an embodied and maintenance energy threshold. Additionally, I have completed an initial panel regression. I didn't have time to talk about that during this presentation, but we did want to mention that we are considering causation as well as correlation to help establish embodied energy as a relevant indicator. And lastly, of course, as with any energy issue, there are policy implications involved that we want to be aware of and informed on so that this research can be applied to create real change in the world. We will conduct case studies on notable countries to inform such policy implications. And with that, that concludes my presentation. I want to thank you for listening today, and I invite any questions that you may have for me.